In this lesson, I am going to introduce you to electromagnetic radiation. So what is electromagnetic radiation? Well, it's really all around us. We've been experiencing it our whole lives. So let's think about this. When you open your eyes in the morning, the first thing you see is light. In fact, it is the only thing you see. In general, what we perceive with our eyes is a combination of many colors, each with varying brightness, but all coming together through the optical system of our eye. It is light, or more broadly speaking, a form of electromagnetic radiation, which produces an image in the human eye. But what is electromagnetic radiation? How is it produced? How is it transmitted, and at what speed is it transmitted? These questions historically have significance. They have guided research and debate over the ages. Finding answers has helped us understand the fundamental principles of our universe and enabled advances in technology in areas such as lenses, fiber optics, digital devices, radios, lasers, global positioning systems, and compact discs. These are all examples of an understanding of electromagnetic radiation. So, what is electromagnetic radiation? Well, before we get much into it, we have to go over some definitions. So first of all, I need you guys to copy down this part here. Frequency. You have to know what frequency is. Frequency is the number of cycles per unit of time. The next one is wavelength. Wavelength is the distance between adjacent points that vibrate in a phase with one another. And another definition you need to copy down is electromagnetic radiation. Well, electromagnetic radiation is radiant energy in the form of a wave that is produced by the accelerated electrons or other charged particles. Electromagnetic radiation does not require material or a medium. It can travel through a vacuum. So that's a key thing. Very different than sound, which cannot. Electromagnetic radiation can actually travel through a vacuum. So now we're going to look at the electromagnetic radiation spectrum. You guys have looked at this a little bit before in previous grades. Here we're going to have to understand all the types of electromagnetic radiation in the spectrum. We're going to be looking and studying radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. If we look here, my frequency and wavelength are inversely proportional. You will have to remember either the wavelengths range of each of these or the frequency wave range of each of these. So if we look closer, here we have Roy G. Biv, which you guys have been doing since grade 8. Now if we're looking at Roy G. Biv, we're going in order of what? Are we going in order of increasing from wavelength, or are we going in order of increasing from frequency? In this case here, if we look closely, my wavelengths are getting smaller. So that means my frequency is increasing. So if we're thinking of Roy G. Biv, we're going to have to probably think of our frequency increasing. So, electromagnetic radiation is simply radiant energy that travels outward in all directions from its source. So it follows the radius from the center of the source outward. Okay? So, there are different types of electromagnetic radiation that we must become familiar with. And we have to know the order of these electromagnetic radiation, because this will help us determine our energies and so on and so forth. So a way to remember this is raunchy mushrooms in vinegar usually excrete glue, where our small frequency is going to be on my left side and my high frequency is going to be on my right. So raunchy stands for radio, which is the largest wavelength or smallest frequency. Mushroom stands for micro. I is for infrared, V is for visible, U is ultraviolet, X is for X-ray, and G is for gamma. So, types of radiation and what they do. Let's take a look at this. First, we have radio and radar waves. Okay, here is their wavelength. This is needed. We have them. Okay, this is their wavelength. Their energy is very low. Since they have a very low frequency, their energy tends to be very low. So oscillation of electrons in an electric circuit like an antenna. So characteristics are long wavelengths, allows for large amount of diffraction, making it useful for long distance communication. Problems: it requires government regulations to control transmissions and avoid interference because it's very interfere with radio waves. The next one we're going to look at are microwaves. So microwaves, they are slightly higher frequency, but still on the low end of radiation or low end of energy. So oscillations of electrons in special tubes are solid state devices. Shorter wavelengths reduce diffraction for short distances communication. Frequency match the natural resonant frequency of water molecules used in microwave ovens and cell phones. It may be linked to some forms of cancer or some problems. It causes damage to living tissues due to heating of water molecules within tissue. Our next one we're going to look at is going to be infrared. So infrared, still a lower level of energy. We're just getting a little bit higher frequency now and shorter wavelength. So what are these? This is the motion of particles, transitions of valence electrons, atoms, and molecules. So it's the movement now of particles because that's heat, and infrared detects heat. So it causes object absorbing it to become warm. Uses for remote sensing, night vision scopes, identification of sources and heat. So some problems are significant exposure can burn our tissue. Next, we're going to look at visible light. Okay, so this has a bit more energy because our frequencies are larger and our wavelengths are getting smaller. So higher energy transitions involving valence electrons. So we're going to learn about this, valence electrons jumping and what light they give off and something like that, or what kind of electromagnetic radiation they're going to give off later. So basically they reflect off small objects, making them visible. It diffracts around very small objects, making them invisible. A problem with it though is it limits the size of objects that can be seen. Not all things can be seen with visible light. Next is ultraviolet. So now we're looking at things with high energy. Okay. So our valence electrons can even give off ultraviolet radiation. So it's higher energy transitions involving valence electrons and atoms. It's easily absorbed by objects, causes fluorescence of some materials, tanning in humans, and kills bacteria. Now some problems with this are it can cause sunburn. Prolonged exposure can cause mutations such as cancer in humans. Then we're going to go into X-ray, which is very high energy. So it is transitions of electrons in atoms or the sudden acceleration of high energy in free electrons. So this penetrates most matter and is absorbed by denser materials like bone, metal, and so on. It destroys carcinogenic or mutated cells. It is used for medical imaging and humans in the industry. Because if we think about this, a lot of us have had x-rays before, and we use that so we can see past all the tissue and see our bones, see if there's something broken. But it doesn't really help with our muscles, the x-rays, because it sees through that, so we need something else to see the muscles. And we'll be learning about that in MRI machines a bit later in this class. So some problems with it is it can cause mutations and cancer in humans. So yes, it may kill carcinogenic or mutated cells, but it also creates it itself. Now our last one is gamma radiation, or second last one is gamma radiation, which is extremely high energy. It is the decomposition of unstable nuclei either spontaneously or by sudden negative accelerations from high energy particle accelerators. It penetrates matter very deeply, destroys carcinogenic or mutant cells on a local scale. It's used to probe structures of matter and industrial imaging. Now some problems is it could cause radiation sickness and death. So we use this actually quite a bit, gamma radiation. We're going to learn more about it later, and I encourage you to read about it more in your book. The last one here is cosmic radiation. So cosmic radiation is we get mostly in space, okay? So the bombardment of Earth's atmosphere by extremely high energy particles from space. Earth's atmosphere kind of takes most of this up. It penetrates matter very deeply. A study of the cosmic rays allows investigators to formulate ideas about the universe. So it can cause radiation sickness and death. So if we break down the words electromagnetic radiation, we can think of what that means. We have electro for electricity and magnetic. This is kind of why it comes after our electricity unit, then our magnetic unit. Now we're looking at electromagnetic radiation. So there are two components of this. We have our magnetic component, which is this green here, and we have our electric field component, which is this red. Now the neat thing about these is both of these propagate perpendicular to each other. Okay. So what I want you to do now is, for your homework, and you want to have some class time to do this possibly, you are expected to be able to compare and contrast the different parts of electromagnetic spectrum. You should be able to tell me a few key things about the spectrum. So you're going to make a poster describing the key things such as wavelengths, frequencies, energy, strength, practical uses, where they come from, and what it looks like.